started on indoor air quality as the next topic that we're going to approach, because a lot of industrial hygienists, even if they're working for companies that do asbestos work, lead work, and so on and so forth, they also get calls and are and find themselves doing responding to complaints about indoor air quality. Let me get started. You should be able to see a PowerPoint presentation. It's actually Apple Keynote that I prefer to use. In the 70s, if you go back 30 years, 30 or 35 years or something like that, and further, nobody cared about indoor air quality. Indoor air quality was concerns about indoor air quality were virtually non-existent. They really didn't come up very much. What everybody was concerned about back in those days was ambient air quality, outdoor air, because we had a lot of sources of pollution for outdoor air. This again, we're taking a look at what outdoor air should be composed of. We played around with this last week in terms of uh, uh, what the composition of air is, and so on and so forth. Notice carbon dioxide again is highlighted down here. It's 350 ppm average worldwide. Actually, in reality, probably it's a bit higher than that now, because this was I think I made this up a few years ago. So CO2 levels, as we know, are increasing because of the use of fossil fuels and so on and so forth. So this is what air is supposed to consist of. Unfortunately, air has a lot of other stuff in it. A lot of that stuff is source. A lot of that stuff is vehicular traffic, trucks, diesel exhaust, burning of fuel in New York area. Burning of fuel usually means heating systems and so on and so forth. So there's a lot of materials in the air that are objectionable. In 1970, the United States established a national ambient air quality standard, and that is a series of priority pollutants that get into the air that they decided should be regulated. Okay, that included carbon monoxide, lead, nitrous oxides, dust, particulate matter, grease, ozone, sulfur dioxide, and so on and so forth. Carbon monoxide, obvious, automotive exhaust, and so incomplete combustion of other things. Lead, again, obvious. Back in those days, vehicles used leaded gasoline. They added tetraethyl lead to the gasoline to make it burn more evenly in combustion engines in cars and trucks. Nitrous and sulfur oxides, burning fuels, and so on and so forth, produce those. Automotive exhaust produce those. Sulfur dioxide, in particular, a large source of that was the burning of high sulfur oils and coals. And that material got into the air and would cause respiratory problems. It would also cause a phenomenon called acid rain, because these are acid gases. When they get dissolved in rainwater as it comes down, the pH of the rainwater drops, and it can actually do a lot of damage. Ozone, because it's a respiratory irritant, and so on and so forth. And they established these standards. They've added on to them since then and refined them. For instance, they're focusing now on particulate matter, which is not just total particulate matter, but particulate matter that's small enough that it can be inhaled deeply into your lungs. In other words, respirable particulates, and that's why they split up two standards at this stage into PM10, or particulate matter less than 10 microns, and particulate matter less than 2.5 microns. So this is National Ambient Air Quality Standard, and many times in large cities, the National Ambient Air Quality Standard is exceeded. However, it's not always exceeded the same way. We have an LA style smog here, and we have a New York style smog here. They look the same, kind of, right? But they're significantly different. In Los Angeles, the primary culprits that they're concerned about are ozone and chemicals in the air that are affected by ultraviolet radiation, photochemicals. They, in fact, regulate the use of a lot of materials in LA, solvents, even charcoal lighter fluid, and so on and so forth, because it gets into the air. It's affected by ozone and by sunlight, and so on and so forth, and it produces a lot of objectionable compounds. New York style air, well, our problem is not so much ozone and some other materials, so that does come up occasionally. Our main problems, anyone want to guess on that sheet? what would be our two main problems right now in New York? Somebody hazard a guess. Of those things, what do you think are the main issues, the places that we exceed most frequently in New York? Particulates, good. Thank you, Anand. Hydrocarbon particulates, particularly diesel exhaust, fossil fuels, and so on and so forth, soot, basically. We frequently exceed that. And we've been getting better at it recently, but I think that's more a function of the vehicles they've been selling have been operating a bit cleaner. How about the other one? Also associated with burning, and that's carbon monoxide. Okay, we on occasion have issues with carbon monoxide because of so much vehicular exhaust and truck exhaust and so on. Okay, so those are the problems that we dealt with back in those days. Now we didn't worry about them too much because we thought they were going to go away because we thought that nuclear energy was going to be the saving, was going to save us from everything. There was an expression in the early 70s this that electricity, because of nuclear plants, the proliferation of nuclear plants in the United States, would be so cheap that it might even be too cheap to meter. Okay, well, we noticed that that didn't really happen. We instead wound up with 3 Mile Island, which basically shut down the nuclear industry in the United States. There are very few plants that opened up after the accident at 3 Mile Island. However, we still were stuck with these outdoor air pollution problems, and we've been dealing with them ever since. However, the other thing that happened in the 1970s, is that OPEC, the Organization of Petroleum Exporting Countries, got together and started to set limits on the amount of petroleum that they were sending, that they were producing. And what happened is it drastically affected oil supplies in the United States and in Europe and so on and so forth. And gasoline prices, gasoline was non-existent in some places in the United States, and the prices skyrocketed, caused a lot of issues here. So there became a lot of concern about not just ambient air quality in terms of burning fossil fuels, but also in terms of the availability and the price of a lot of these resources. Okay, so we started to look more seriously at energy efficient design in the United States, meaning ways to conserve fuel, basically. Well, the first thing that people recognized is a tight building is an efficient building. If you heat a building, well, if you keep that heat inside the building, you can save a lot of money. If you allow the warm air in that building to escape and be replaced with cold air from outside, or conversely, if you in the summertime are cooling a building and allow cool air to escape and warm air to enter the building, well, it's going to wind up costing you a lot of energy dollars. It's going to wind up costing the country a lot of oil imports and so on and so forth. So engineers started to design towers that were completely closed up, glass enclosed towers, non-openable windows, some small fresh air intakes, a limited amount of exchange with outside air, with the idea that they'd be able to save an enormous amount of energy. And they did save a lot of energy. The only problem is that as we got into the late 70s and the early 80s, we started to see a phenomenon that started to turn up. And in the newspapers, on the news, and so on and so forth, we started to hear stories about something called sick building syndrome. And this was a term, basically, I guess, invented by the press. It's not a scientific term to describe buildings where they had a large amount of complaints about indoor air quality. People were feeling ill, had a whole range of different kind of complaints, and so on and so forth. And they started to call those sick buildings. They also started to notice, once they started paying attention, that there were certain kinds of illnesses that were related to building environments as well. Allergies, certain kinds of pneumonias, certain kinds of respiratory illnesses, and so on and so forth, asthma, and so on and so forth, that seem to be related to indoor environments in some ways. We're going to get into that more as we go along. So basically, a new science started to develop, the science of indoor air quality. Before the 70s, there's very little research on indoor air quality. So first thing you got to do is you have to start to talk about what's an acceptable indoor environment. In other words, if you're going to define what's not acceptable, You also got to spend some time thinking about what's acceptable. Some of it's obvious, like lack of offensive odors, comfortable temperatures, comfortable humidity, comfortable amount of airflow, and so on and so forth. But we're going to be talking about some of those as we go along. ASHRAE and a few other organizations have in the interim attempted to put together some basic guidelines that suggest some numbers that might be associated with good indoor air quality. A lot of these are comfort related, like you'll see over here for ASHRAE. The first three things are humidity, temperature in the summer, temperature in the winter. You'll notice carbon dioxide comes up there, and carbon monoxide. Well, carbon monoxide obviously is an issue. Ozone is an irritant. Dust or particulates could be irritants. Lead is toxic. Formaldehyde. If we'll talk about formaldehyde, formaldehyde is present very frequently in certain kinds of building materials, particularly composite materials, press board, furnishings, and carpeting, and so on and so forth. And formaldehyde, in particular, is present in new construction materials. You probably don't see too much of it now because most people have caught on to this and they've started to move to low VOC emitting materials. In other words, they buy carpeting, they buy furnishings that are certified to have a lower level of off gassing of these various kinds of things. But I'm sure you guys have experienced, maybe not recently, but have experienced walking into a newly furnished office with new carpeting, and for the first 3 months that you're walking in there, your eyes are watering, or you're smelling kind of a strange acrid odor, and so on and so forth. And those are off gassing of materials from paints and carpeting, and so on and so forth. Fortunately, there's less and less of that as people have kind of become aware of that. It's still kind of a bit of a problem in the mobile home industry because they tend to use a lot of these presswood materials and urea formaldehyde foams and so on and so forth, the materials that sometimes break down in high heat or humidity. And it was a problem with the mobile homes that they initially had installed after Hurricane Katrina in New Orleans. But we can spend more time on that maybe in one of the future lectures. So we needed standards. The OSHA standards, they weren't much help. For instance, carbon monoxide, 50 ppm. That's a lot of carbon monoxide for what would be otherwise a relatively clean air environment. The odors, the other things that are associated with 50 ppm levels of carbon monoxide would probably be intolerable in a office environment. You probably smell so many other things that went along with it that it would be really too unpleasant. Or hydrogen sulfide, your nose is sensitive enough to smell hydrogen sulfide at less than a part per million level, and having 20 ppm of something that smells like rotten eggs in an office is probably not going to be very satisfactory for the people working there. However, these are meant for different. In other words, it's very difficult to apply the OSHA permissible exposure levels to environments where people expect the air to be cleaner, or where you'll have a population that is different than the originally intended for the PELs. For instance, 50 ppm in a working environment where you might not expect to have pregnant women might be somewhat tolerable, but in an office environment where there might be children present, might be a daycare center, there might be pregnant women, there might be people with respiratory problems, with heart problems, and so cardiovascular problems. 50 ppm is kind of a stretch. So ASHRAE's limit is 9 ppm on the other hand. Notice there's a lot of stuff that's not included here. Many, many things that could be in indoor air that are not mentioned here. And there's other standards as well. So I'm going to move on from there. So there are standards around. They're very difficult to apply because they're not really definitive. There isn't really a single governmental standard for things that might be in indoor air. So a lot of what you wind up doing is based on whatever standards you can find and on experience having done these things for a while. Okay, good. So just so you know, guys know, I am recording this, so if you wind up missing this or have to drop out or came in late or something like that, you should be able to go back to, assuming that the technology holds up, you should be able to go, which is not always the case. You should be able to go back to this. ASHRAE, American Society for Heating, Refrigeration, and Air Conditioning Engineers, is an engineering society that has published many standards regarding air conditioning systems and air handling systems in commercial office buildings and so on and so forth. There's a few of them that are particularly of interest to us when we're looking at indoor air quality. The first one is filter type devices. 52.2 is for standards for filters on HVAC systems. 55 is for thermal comfort. In other words, what temperatures are acceptable. 62-1 is ventilation rates in buildings, air movement, how much fresh outside air you should have, and so on and so forth. And ASHRAE standards this ASHRAE standard in 1970 permitted much lower levels of exchange with outside air than it does today. Notice this is the 2010 version I reference here. I think there might even be a more recent one. Okay, and that's what these standards look like. You can actually go on their site and download them. I might be able to come up with some of them for you. Technically, you're supposed to buy them. They're proprietary standard and not an open standard. So they actually sell these on their website. But there's certainly elements of it that I can excerpt that are important that we can take a look at when we need it. For instance, comfort. In general, ASHRAE says that summer and winter, you want a range of 30 to 60% humidity. You don't want the air too dry. And you want two different temperature ranges for summer and winter that they consider a range that most people will find comfortable. Not everybody, but most people will find comfortable. And that can range from 68 up to the high 70s, depending on the time of year. Wintertime, they have a lower range that's acceptable because people are generally wearing more clothes in the wintertime than they are in the summer, and so on and so forth. Also, for energy considerations as well. Anybody want to hazard a guess what the humidity probably is right now in your homes? I'm gonna hold out every once in a while for somebody to give me a response for two reasons. One, so that I know you're awake, and two, so I know that this is all still working since I can't see you and get direct feedback. So I'll wait you out. So you're gonna have to respond. Okay, somebody's saying 60, 50%. No, chances are the humidity in your home right now is probably under 20%. Could be 10%. The air, unless you're humidifying, the air in your homes right now is very dry. The reason for that is that air, depending on its temperature, can hold a different amount of moisture. Now, air that's if it's 50% humidity outside at 30 degrees, when that air comes into your home and you heat it up, the amount of moisture that it can hold is much higher. So, relative to the amount of moisture that it can hold, it has the same amount of water in it, but relative to the amount that it can hold, it might only be 20% or 10%. And we're notorious for having very low humidity that can affect artwork, can affect furnishings, and so on and so forth. That's why you see museums, hospitals, so on and so forth, purposely humidifying the air in the wintertime. As far as homes are concerned, not many people humidify their homes unless they have unpleasant side effects from dry air, or they're storing something valuable that requires humidification. They're growing orchids. I don't know. I guess there's a lot of reasons. Not too many people do it, and very few office buildings humidify the air in New York City in the wintertime, unless they're doing it for. Well, if your windows open, remember you're still bringing in cold air and heating it up. So you're probably not helping much. What might help is buying a humidifier or maybe putting a pan of water on the radiator or something like that. So you're evaporating some water. You boil a pot of spaghetti, that's going to throw water into the air. So you need something. Bringing air in from the outside. The air is already dry because it's a very low temperature outside. When you bring it in and warm it up, the relative humidity, now relative means how much humidity it can hold, drops even further. Okay, so and dry air is an issue, and like I said, most office buildings don't bother to humidify because it takes a lot of energy, except in certain circumstances. And those circumstances are typically if they have a data center, because electronic equipment is very sensitive to static, and static is more of a problem in dry air. Also, devices that have to do printing and paper feed and stuff like that have issues with static, and so on. So generally, you'll find a lot of places that in New York that have issues with dry air in the wintertime. So I did all sorts of general complaints, and trust me, when you get into air quality, they blame every kind of complaint on every kind of like odd odor or odd feeling or something like that on possibly being caused by the quality in your air. And sometimes they're right, sometimes it is, but a lot of times there's a lot of other issues that are involved here that involve workplace stress and concerns about health concerns that may or may not be related to indoor air, but in people's judgment, they really can't separate them, and so on and so forth. So it is a difficult thing to manage, and to convince people, and to convince people that they may have an issue in one area, or they may not have an issue in another area. Okay, so in order to do indoor air quality, we got to understand building systems. Okay, mostly the way building systems operate. I wish I could use a pointer here. Is there a way for me? I don't think so. Um, Building systems typically, unlike your home, which unless you have a forced air heating system, an air conditioning system, you may just have a radiator or a convector, convection piping or something like that that heats your home. That's just using steam or hot water radiating from a pipe or a radiator or something like that. That's sending heat around your home, and you may have window. A lot of people, most people have window unit air conditioners, but a few of us have homes that have central air conditioning systems where they're actually moving air through ductwork. The typical commercial office building almost always has that kind of system. So you see one illustrated here. When we were in the lab, we could see the diffusers were delivering air into our space from an air handling unit. That air handling unit in the wintertime has coils in it that run steam or hot water through them so they can heat the air so that it reaches our space warm. Or in the summertime, they have coils in them that can cool the air. That can either be a refrigerant like Freon, or it can be cold water that's chilled by a device in a central plant and then piped over to that air handler. Okay, so you can see the air handler is filtering. There's a little filter at the beginning of that too. They don't show here. The air is going through that air handler. It's being distributed to the office. Then it goes back up into the ceiling again and returns to that air handler. That's the purple stuff you see. Some of that air goes back to the air handler. You see the purple line there, the arrows, is actually where it turns up at the very end for relief. Some of it actually goes down back into the air handler. In fact, probably 80 or 90% of it goes back in the air handler. Some of it spills out outside of the building and is replaced with outside air that you see to the far left there in that light blue color. Okay, so that's our air exchange. If that relief and outdoor air intake were not there, we'd be recirculating the same air over and over and over again. And all that body odor and food odor and perfume and so on and so forth would build up inside the space. So that ventilation, that exchange with outside air, that dumping of indoor air, a little bit of indoor air, and pulling in of outdoor air helps us dilute any contaminants that are there. We know that dilution ventilation is not a great way to not a very efficient way to control contaminants, but most of the time in office facilities, that's the only way we have. The guy in the far right that's working in the lab there, he's got an exhaust hood, so he's got a little bit more efficient way of doing it, with a smaller fan. The rest of the place is dependent on dilution ventilation. Okay, of course, these systems can get very large. That's a large air handler on the roof, supplies an entire floor distributed throughout the building. Here's what the inside of an air handler might look like. Starting at the left, you can see a large fan. You can see that fan is pulling air towards the left. And if I go further to the right, you'll see a UV lamp. You don't see that in too many systems. That's meant as a disinfectant for the interior of the air handler. That's a little uncommon. They show it there. And right next to that, you see two banks of coils. One, you see these bright copper tubes on. There's another one next to it behind it that is made out of steel that you can't see the bends so easily. One of those is likely to be a steam coil for heating. The other one is a chilled water or a refrigerant coil for cooling. Might have Freon in it or might have cold water. So those two butted coils are the way that you control the temperature of the air. And if you go back further, you see a filter system. They call that bag filters. You see those as it's referred to as bag filters. That's because they kind of look like large bags that are open to the air on the right, and as the air gets sucked through them, it gets cleaned before it goes to those coils and to that UV light and to the fan. And then finally, at the very end, you have a damper on the outside of the building. If you look at the small version up there in the top corner with the little man there, you can see the far sides. You can see kind of a Venetian blind kind of thing, and that's the damper. That controls how much outside air is coming in that's mixing with the recirculated air that's also going into the beginning of this air handler. Those units you see at the top are exhausts, how much exhaust air is being dumped out while you're pulling in that fresh air as well. So that's what an air handler, that's what a big air handler looks like. And I'm hoping for in addition to doing some exercises with some instruments to test indoor air quality, that we're going to get a chance maybe to get a tour of the air conditioning system in the building that we're in at 119th Street and 3rd Avenue. But they gave it to me. They did it for me 2 years ago. I wasn't able to get to do it last year, but I'm thinking I can be successful this year. When you have a home unit, this is probably what a home unit looks like. You have a vertical unit. It's got a little heating, a gas heating device on there and a heat exchanger. You blow air through the heat exchanger so you don't mix it with the actually burning gases. Goes up into the house, comes back down through a duct, probably on a wall somewhere, all the way back down to the unit, and it's recirculated over and over again. And notice there's like many home heating units, it doesn't have a fresh air intake. There is a little flexible metal duct coming out of the top of it and going to the left, small round one. That's an exhaust for the exhaust gases from that burner that's in the bottom. Okay, that's not a fresh air intake. Okay, now a lot of you guys have just to talk about how refrigeration units work. A lot of you guys have um, 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 a lot of you guys have window unit air conditioners, and the way that they work is they use a Freon refrigerant, and that Freon refrigerant is metered into a coil. If you look at this, you see in the right side is the front of the unit, which is inside the house. The left side is the back of the unit, which is outside of the house. You see a fan there, you see a condenser and evaporator. Those are two coils. I'm going to show you those two coils here. Okay, there's the coil, the condensing coil, and the evaporator coil. Unfortunately, here they're reversed. The inside of the house is on the right. Okay, so now the evaporator coil takes liquid Freon that's fed into it through that little capillary tube that you see at the top there. Little bit of liquid Freon is metered into that coil, and the Freon evaporates at a very low temperature. So what happens is the coil becomes very cold. A fan blows air into your house over that coil. So that coil cools the air in your home. And then you blow air into the home, and then it's got a little vent usually on the bottom, pulls air back over, so you're continually recirculating air over that evaporative coil. Well, problem is that now you've evaporated that Freon in the cooling process. You've turned it into a gas. So if you go down on the bottom, you see that light blue color that goes back to the compressor. That Freon gas, hot Freon gas, that Freon gas goes back to the compressor. The compressor is a device that takes the gas and, as the name implies, compresses it. Either uses a piston or a centrifugal device to compress the gas, and it compresses the gas so that it compresses it so it's a very hot. You know, when you compress gases, they get hot. So it's very hot. It's still a gas, but it's very hot. So now you have to change that back into a liquid so you can reuse it. So what happens is that there's another coil at the back outside the window called the condensing coil. The fan is blowing over that condensing coil. Those hot Freon gases, when the fan cools them off, they condense back into a liquid, hence condensing coil. And then there's a little expansion valve at the bottom, that dark blue thing, which then meters it back in the capillary tube, keep the whole thing going. That's how this thing works. So you can reuse that Freon over and over again. And if the condensing coil gets dirty, well, it can't get rid of the heat, so your unit won't operate anymore. If the evaporative coil, the filter, gets dirty, well, then the air can't flow over it, and so on and so forth. So you have issues with it there. But that's basically how this process works. Okay, and many of the operations that we see for cooling, even in giant buildings, work very much like this, except that in a giant building, instead of the evaporator having a fan blowing over it, it might be sitting inside of a large shell and tube device, where it's actually not cooling air, but instead cooling water. And then that cold water is piped all over the building, so it can be pumped through coils that you blow air over locally, and cool the air that way. On the other hand, there's many buildings that use giant evaporator coils, just blow air over them and then duct the air all over the building. So you're going to find that every building you go into is going to be slightly different. Okay, so that's how that works. I'm not going to get into too much detail, but heat pumps, the way that they work, remember that window unit air conditioner? You got hot air blowing out the back of it because you're taking hot air out of the air. You got cold air blowing out the front of it. If you took that unit and turned it all around, you'd be blowing hot air into the house. So you could use outside air, even if it's pretty cold outside air, you could use outside air to heat the air indoors. Heat pumps do exactly that, except they do it with valves. So the evaporator coil now becomes a condensing coil and provide heat to the home. And the evaporated condensing coil becomes the evaporative coil. So you absorb heat from outside to move heat into the building in the wintertime, or move heat and change the valves again and move heat outside in the summertime. Okay, here's another building system. You'll notice that in the basement, they have chillers making chilled water, and that chilled water is pumped to air handlers throughout the building to cool air. There's also a boiler there to send hot water up to other coils in air handlers throughout the building on each floor. So you can heat the air or cool the air as you need it and send it to these diffusers throughout the building. At the very top of the building is a cooling tower, and we're going to talk about cooling towers later on when we get a chance to when we'll get into the issues of air quality and so on and so forth associated with them, specifically Legionnaire's disease and other microbial issues. Okay, so I have a bunch of terminology. I'm going to put up I'm going to make sure that last week's stuff is posted. I know I have been having problems getting stuff onto Blackboard, unfortunately, but I think that's worked out now. It seems to be stabilizing. But I'll get this presentation and some other materials from last week posted on Blackboard, including the PowerPoint from last week, so you guys have a chance to get through that stuff as well and see this stuff. We have a lot of reference materials in here too. So indoor air quality. We just talked about one of the most important elements of indoor air quality: control contaminants in the building. The one real way that you have control, and that's exchange with outside air. Okay, and here's another illustration of a unit where you have some of the air is recirculated and some of the air is returned, and you can control how much is recirculated. This system, 100% outside air is coming in. Actually, some hospital suites use this. Certain operating rooms, they use high efficiency filters, and they all use once through air. Endoscopy suites and so on and so forth use 100% outside air and so on. You can imagine the odors there, so you want to control those. Okay, so now let's say you're called on to evaluate the air. How do you go about doing that? There's a lot of issues here, not the least of which is that there's not a lot of good standards that you can rely on, or not a lot of really definitive standards. So here we take a look at the air from certain perspectives. The first thing we do is we evaluate the ventilation without. First of all, the first thing we do is inspect the HVAC equipment, so we get an understanding of how it works. How is it supposed to work? Is that reasonable? Is the equipment working properly? Is it in good condition? Is there stuff that's not working? Dampers not opening, outside air dampers not opening, and so on and so forth. And then we use measuring equipment. You've already had your hands on some of this measuring equipment that we use. An anemometer that guy's using to measure the flow in that duct. A bolometer used to measure the amount of air coming out of the diffuser. And then we want to measure, again, we're measuring the ventilation with outside air. That's pretty cumbersome, though. You saw how much trouble that was to do it with a duct that's sitting right out on the table, let alone one that might be 20 feet up in the air. One of the ways that we estimate the amount of exchange that we have with outside air is by measuring the carbon dioxide levels inside the building. And the idea there being, and you saw that referenced briefly in one of those ASHRAE standards, the idea there is that if outside air has 350 or 400 parts per million of carbon dioxide, and you go inside and measure it indoors and it's higher than that, how do you account for why it's high? Why would it be higher than outside indoors? Somebody want to give me an answer to that quick question? Can I get an input on that? Sorry to wake you. Come on, I know somebody out there knows. Give me a guess. Why would CO2 levels indoors be higher than they are outdoors? I'm gonna wait. I got time. Okay, good. Okay, I got a slurry of answers then. Okay. Well, the air doesn't move around that much, lack of circulation. The real reason is that because human breathing. Thank you, Dave. Exactly. People are breathing into the air. People breathe in oxygen, they burn it, they exhale carbon dioxide. They're adding carbon dioxide. The main source of carbon dioxide, when you could get carbon dioxide from combustion products, but that means something's wrong. That means your furnace is not venting properly. Something very serious is very seriously wrong. Most of the reasons that you get carbon dioxide buildup inside of buildings is because people are breathing into the buildings. As you get people breathing into the buildings, the CO2 levels go up. Now, the only thing that'll take that out is dilution with outside air. So ASHRAE has worked out that if the levels indoors are more than 1,000 parts per million higher than the level outdoors, or excuse me, 700 parts per million higher than the level outdoors, or say roughly higher than 1,000, that would suggest you're not getting sufficient exchange with outside air. Okay, and that's based on their, for instance, their standard. That standard that we looked at before that suggests in an office environment that you should get 20 cubic feet per minute per person of exchange with outside air. Different amount in school, different amount in an auditorium, and so on and so forth. But for an office building, they say 20 CFM per person. And if you're really getting 20 CFM per person per minute of exchange with outside air, you shouldn't exceed more than 700 parts per million of outdoor levels, or about 1,000. Okay, so we can actually measure CO2 levels to make a judgment, not a perfect judgment because we're not measuring it directly, but we can make a reasonable judgment as to whether or not we're getting sufficient exchange with outside air or reasonable exchange with outside air. So one of the ways we do this is we do this with colorimetric tubes. This is a Draeger hand pump, and every time you squeeze it, it sucks. It takes 1/10 of a liter of air and pulls it through these various these rainbow colored tubes at the bottom. Each one of those tubes may be suitable for measuring the concentration of a different gas in the air. Okay, ozone, acetone, so on and so forth, formaldehyde, so on and so forth. In this case, we're looking at a tube that's intended to measure carbon dioxide levels. So on this particular tube, it looks to me like it's reading about 600 or 700 parts per million of CO2 in the air. So we're actually going to do this. We're going to use some CO2 tubes, and we're going to, run around the school and maybe measure some CO2 levels to see if in some of the crowded classrooms we're actually exceeding the ASHRAE standard. Now, I suspect that might be a possibility. Okay, you can also use electronic devices for measuring outside air. These are two examples of these monitors. Typically, they'll, in addition to measuring CO2 levels, they'll also test for carbon dioxide, carbon monoxide, and temperature and humidity at the same time, so you get a bit more information out of it. And the one on the right, as well as we have a couple, I think, at school, that will data log. That over time, you can actually get it to take a reading every minute, leave it behind, and you can then print out a graph of what the CO2 levels were over a period of time. So, does it look like this particular facility is exceeding the ASHRAE standard for ventilation with outside air? Quick guess, quick answer. Somebody give me a yes or no. Are we exceeding the ASHRAE standard here? Okay, I got one yes. Any other yeses? I'd say it's borderline because it looks like they're peaking out at just about 1,000, right? So, as an indoor air quality person, I'd say to myself, I can't really say that they're not getting the required amount of outside air, that they're not getting the 20 CFM per person because they're within 700 ppm of outdoor levels, which I'm presuming for a moment to be 350 or 400. But they're so close that yeah, it's really kind of marginal. You know, you like to see a little bit of a lose. Some indoor air quality people, I won't call them experts. I don't know. I don't know that anybody's an expert in this field, but indoor air quality, for the want of a better expression, some indoor air quality experts suggest that if you're getting over 800 ppm CO2, that you should consider, like, taking another look at the ventilation rates. Of course, people that are concerned with energy conservation would dispute that because you remember, that means you're giving them a lot more outside air than ASHRAE is recommending. So that means you're using more energy. So it's tough. You can also use CO2 as a tracer gas. For instance, you could say if it's at the end of the day, let's say you have a building that closes at 6 p.m. and at the end of the day the CO2 levels are 900 ppm. You could leave a monitor in there and watch after they close the place, have the air conditioning continue to run, and then you could watch how quickly the CO2 level declines. And based on how quickly it declines or dilutes with outside air, you can predict what the ventilation rate is that way as well. Next thing a lot of people are interested in is organic chemicals. Use solvents, you use cleaning chemicals, perfumes, food odors, you name it. There's all sorts of organic materials, new furnishings, carpeting, glues, magic markers are all contributing organic chemicals to the air. We can measure those. We can monitor those as well. Not a lot of standards to compare to, but in general, a lot of people will say if you get over a couple of parts per million, if you get a ppm or a couple of parts per million of VOCs in the air that aren't diluted, then you got to take a look at what the source of those were and if you get enough outside exchange with outside air. So on the right and left here, you actually have devices that will directly measure the amount of volatile organic compounds in the air. We're going to be actually using these when we talk about, when we get to the point where we're going to use photoionization detectors, the device on the left, and multi-sensor units, the device on the right. When we start to get to play around with those things, we can discuss how they work, but you can actually directly read how many parts per million of volatile organic compounds you have in the air. Another way to do it is that they have these canisters. Sometimes some people call them SUMA canisters or T0 canisters because there's a standard called T015 that's used to measure do GC analysis, GC and mass spec analysis of volatile organic compounds in the air. And basically, the way these work is that the lab cleans them out with nitrogen and evacuates them, so they're under a vacuum. And you take them somewhere, you open the valve up, and they suck in the air, and then you give it back to the lab, and the lab then analyzes it using the air that you capture using a GC. They can also put special valves on them, so when you open them up, they restrict the air movement into them, so it can take 15 minutes for them to fill, an hour for them to fill, or even 8 hours for them to fill. So you can get an average reading for VOCs if you want that. There are relatively inexpensive organic vapor badges. These are just basically badges with activated charcoal behind a little diffusion screen, or some other sorbent material, depending on what you're measuring. And you send them to a lab. You wear them for a period of time. You report how long they were exposed to the environment. They're often used for personal monitoring. That's why they got a little clip. You clip them to your collar. You can use them for area monitoring in indoor air quality. You expose them for a period of time, maybe 8 hours if you're doing personal monitoring, maybe a day if you're doing area monitoring. You send them to a lab and they report back to you what the average level of organic vapor, specific organic vapor that they were exposed to. Another way to measure organic vapors in the air is to capture or concentrate the vapors in activated charcoal. Okay, and what we have here is we have a little tube that's filled with activated charcoal. You see there on the left, sorbent tube. That little tube, little glass tube with activated charcoal or some other sorbent material connected to a low flow pump where we suck air through that tube, and the organics get are captured on that activated charcoal. They're absorbed on the activated charcoal. We send the tube to a lab. The lab knows how long what the flow rate was, how long we ran it, how much air was pulled through it, and it can report to us how much of that material that it absorbed and how much that meant was in the air. And then they actually run it on a machine that produces peaks for gas chromatograph that produces peaks that indicate what compounds are there, and the area of those various peaks indicates the concentration of those compounds. We actually have a student GC in the lab that's not working right now, but maybe before the end of the semester we get it working. But we're actually going to do some measurement like this and send a few samples off to the lab. So we're going to get a chance to do that as well. The other thing that we see in indoor air quality is dust. A lot of issues with dust. Dust, you can actually, there are many different materials that present as particulate matter. Everything from pollen to construction dust to asbestos to lead dust from paint to smoke to dust viruses to bacteria to fungal spores, so on and so forth. Those can present in the air as dust. You can actually capture that material. This gives you an idea of relative sizes. Okay, again, we're most concerned about respirable dust, and we can capture that in the air using devices like this. Let me go back here. Okay, see there's a little filter cartridge there, filter and support pad. That plastic canister has a filter in it, and we can pull air using the black pump, suck air through it, and capture the dust that's in the air using that device. That aluminum thing called a cyclone that's underneath it pulls air as it's sucking air, pulls it in there and spins it so that large particles are captured in that device and wind up down in that little grit pot on the bottom. And only smaller particles smaller than 4 microns, actually get through that and get stuck on the filter. So you actually can use that device with the cyclone to measure the amount of respirable particulates that are in the air. And then you can actually look at those particles and try to identify them and do various other kinds of work with them. You can also do wipes and so on. If you use it without the cyclone, you're measuring total particulates because there's nothing there to sort out the size of the particulates. This is kind of what it looks like. It's got a support pad so that you don't break it as you suck air through it. And then there's the actual filter itself. In order to measure how much particulate there is, we weigh it. We weigh the filter before, weigh the filter after, and the difference is the milligrams of particulate, and then we convert that into how much would have been present in a cubic meter of air for milligrams per cubic meter. There are also direct measuring devices, usually optical type devices, that will measure in real time with a display the amount of particulate matter that's in the air. Another thing that we wind up examining in indoor air quality is mold. Mold, of course, is an enormous issue now because a lot of people are attributing, rightly or wrongly, there's a lot of research that remains to be done, are attributing a lot of indoor air quality issues to mold. This is a really extreme issue that this could have been flooding from Sandy or from Katrina. You know, that building materials are affected. You know, the paint, the paper on wallboard are all materials that mold will grow on and consume, will eat. You know, and you could wind up with if you leave an area that has these kinds of materials unprotected and wet for long enough time, you can start to grow mold on. And this is a really extreme case of that. Well, how do we measure that? One of the ways, New York City Department of Health has a standard for the assessment and remediation of mold. And they actually don't encourage testing for mold. They encourage inspection for mold. Okay. And if they saw a situation like this, they wouldn't say, oh, we got to get a few samples. Let's take some air samples. Let's do this and that. What they would say is, we have mold. This is a problem. We don't really care what kind of mold it is. What we care about is how much there is. And since, assuming the whole room is like this, since we have more than 100 square feet of mold, we are going to abate this with great care. We're going to contain it with plastic. the room with plastic. We're going to keep it under negative pressure. The workers are going to be trained. They're going to use respirators, and so on and so forth. They're going to completely abate this, and they're going to throw it away, kind of like an asbestos project, except that the waste can go into the garbage when you're done in plastic bags. It's not considered a hazardous waste. You don't have to send it to a special landfill. But they have recommendations based on the amount of material. If this was only 2 or 3 square feet of mold, like a corner that was a bit moldy, that would just be basically a maintenance issue, and it would have kind of recommendations that maybe the worker should get some basic training, and maybe he should wear goggles and simple dust mask and N95 mask, and take certain precautions, to avoid getting the dust around, the mold around, and handle it that way. Maybe do a little bit more if it gets over 10 square feet, a little bit more if it gets over 30 square feet. And then as it gets more and more, it's based on not what kind of mold it is, because not a lot of agreement about which molds are really bad and which ones aren't bad, and not on a lot of testing either if you can see the mold, but rather on how much do you have and how do you, to determine how you handle it. Okay. Now, if you do want to do testing for mold, maybe there's environments where you're not sure if there's mold there, what kind of mold there is. Maybe it's in areas hidden you can't get to or something like that. There are various sampling devices. This one's called an Anderson. They call it an E6. My recollection is that we've been calling it an N6. It's a 6 stage of an Anderson sampler. You put a petri dish in there. You pull air through it, and it impacts air onto the petri dish. You incubate the petri dish. You wind up with something like in the lower left-hand corner, and then you look at it under a microscope, and you're trying to identify what kind of molds were present and how much mold was present. Okay, this is another way you might measure the amount of mold in the air. Is these things are called spore traps, and basically what you're doing there is very similar to particulate testing, except instead of a filters, these have like a little sliver of plastic with a sticky material on it, and you suck air through it for 10 or 15 minutes. Any particulate gets stuck to it. Some of that particulate is going to be pollen, some of it's going to be dust, some of it's going to be skin cells, some of it's going to be mold spores. And a microbiologist at the lab then looks at this and actually counts how many mold spores and tries to identify what type they are. And you can use that to get a judgment as to how much and what kind of mold is present in the air. Okay, generally they're using those comparatively. Do you have more mold inside the house than you have outdoors? Do you have more mold in an area where you think you might have a problem versus where area you don't have a problem? The reason why you do that is because no hard standards on what numbers. Then, of course, you can do bulk sampling, like on the left hand corner, swabs. On the bottom left-hand corner, that guy's doing a tape lift. He just sees something he suspects is mold. He puts a piece of clear sticky tape down over it, pulls it away, sticks it into a bag, and sends it to the lab for the lab then analysis. The upper right-hand side, they're doing a bulk sample. He's actually scraping a piece off. And anybody know what that instrument is on the bottom right-hand corner? Okay, time to wake up again. Give me a guess on what you think that instrument is on the bottom right hand. That's a moisture meter. Thank you, Anand. You've done this work before. Anybody want to hazard a guess? Why did I put a moisture meter in here when I was talking about testing for mold? Somebody besides Anand, tell me why he's using a moisture meter when the problem is mold. Come on, be bold. Take a chance. I haven't yelled at anybody with wrong answers. That's right. Mold grows in areas where there's moisture. That's where we're likely to find mold. Very frequently, when I tell people to do a mold investigation, what I'm telling them to do is do a moisture investigation. Go look where there's moisture. Go look for mold where you see moisture. Okay, the EPA actually has a test they call ERMI, Environmental Relative Moldiness Index. They have a device that you put on a vacuum cleaner, simple vacuum cleaner a homeowner can do himself. You vacuum a certain area of highly trafficked carpeting or some other areas they recommend in your home. You send it to a lab, and the lab compares that to thousands and thousands of other homes that have also done this and rates it on a relative scale on percentiles. So, in other words, you could be in the 90th percentile of moldy homes or something like that, and say, "Oh man, maybe I have a problem here." You might be in 10 percentile. And you may say to yourself, "Oh, okay, yeah, 90% of the homes that sent this in have more mold on this thing when they sent it to EPA than I did. But it's kind of interesting. Get a chance at it. I don't have a picture of it, but it's just a little plastic device you put on a vacuum cleaner. Seems kind of hokey, but they've been getting some interesting results with it. I haven't read anything recently, but it's an interesting idea. The